Hello, in this video we're going to be starting section 6.1, which is on solving trig equations with identities. So we're going to start off by talking about verifying trig identities, which just means that we have an equation with trig functions. We are going to verify it by showing that the left side is in fact equal to the right side. So here are a couple identities. These ones we specifically call Pythagorean identities. To verify them, we are going to show that the left side does in fact equal the right side. So we can do this by simplifying the left side all the way down until we get 1, or if we get stuck, we can simplify this left side as far as we can, and then try and manipulate the right side to the best of our ability to make it match the left side. For our first Pythagorean identity, the cosine squared plus sine squared is equal to 1. I am going to talk about this by using the unit circle. So any point on the unit circle has the coordinates of x, y as normal, but our x value is the cosine of the angle theta that was used to get to that point on the unit circle. So here is theta. So the x value is that horizontal component of this triangle that we can draw up to that point. And my y value is going to be the sine of theta. So this horizontal distance is the cosine of theta, and the vertical distance is that sine of theta, giving us the coordinates of that point on our unit circle. Since in a unit circle our radius is 1, that's what makes it our unit circle, I can draw the hypotenuse of this right triangle to be 1. Well, using Pythagorean's theorem, we know that in a right triangle, a squared plus b squared is equal to c squared, where c is our hypotenuse. Well, in this case, my radius is my hypotenuse, so this is equal to my radius, which is 1, my hypotenuse, to the second power. A squared would then be one of my legs, and b squared would be one of my legs. So I would have cosine theta squared plus my b would be the other leg, which is sine of theta squared, would be equal to that hypotenuse squared. Or simplifying this, I've got cosine squared plus sine squared is equal to 1. So this is one of our fundamental Pythagorean identities. We can then manipulate our theorem, this first identity, to obtain these other two identities that are also considered our Pythagorean identities. If you'd like to take a moment to pause the video and try this on your own, feel free to do that. But I am going to go ahead and walk us through this one, and then I will ask you to pause and try the next one on your own. So my goal here is to show that the left-hand side is equivalent to the right-hand side. So I'm going to manipulate this left-hand side the best that I can to get it down to cosecant squared. Now if I get stuck, then I will stop manipulating that left-hand side and I will manipulate the right-hand side to again get it to match our other side. So I'm going to start by manipulating this cotangent squared function. Cotangent squared I know is the reciprocal of my tangent function. Well, tangent is sine over cosine, which means that my cotangent is going to be cosine over sine. So I have my cosine of theta over my sine of theta. That is my cotangent. I am squaring that. Plus 1 is equal to cosecant squared. So this is cosine squared of theta over my sine squared of theta. So using properties of exponents, if I'm squaring this entire fraction, I can apply that exponent to both the numerator and the denominator. So instead of cosine over sine all squared, I just squared the cosine and the sine individually. Now because I know that cosecant is the reciprocal of sine, I'm going to go ahead and add these two terms by creating a common denominator. So my 1 I am going to rewrite as sine squared theta over sine squared theta. Now that allows me to combine my fractions because I have a common denominator. One reason I did this is because, like I said a moment ago, I know that cosecant is the reciprocal of sine, but also I know that I only have one term over here on the right and I have two over here on the left, which tells me that I need to somehow find a way to combine those two things to make them into just a single term. So here's my first effort to combine those two different terms into a single term. So when I add, I've got cosine squared theta plus sine squared theta all over, and then I keep that common denominator of sine squared theta. Now I can look at that numerator and say that that is an identity that I recognize. Cosine squared theta plus sine squared theta is a very, very common identity. If I go back to what we just talked about on our last page, I see that that cosine squared plus sine squared is equal to 1. So I can use my Pythagorean identity to rewrite that numerator as just 1. So my denominator is sine squared of theta, and that's equal to my cosecant squared of theta. Well, 1 over sine is cosecant, so 1 over sine squared actually becomes cosecant squared of theta, which is in fact equivalent to that right-hand side of my identity. So I have shown, using substitution and algebraic techniques, that this left-hand side of my equation is in fact equal to the right-hand side. Go ahead and take a moment to pause the video and use some similar techniques to prove the statement in example 611. So tangent squared I am going to write as sine squared theta over cosine squared of theta. And because, again, I've got one term on the right, I'm going to add these two by creating a common denominator. So the 1 I'll write as cosine squared over cosine squared. Adding those things on the right-hand side, I keep my common denominator, and I've got cosine squared over sine squared all over cosine squared. And the Pythagorean identity tells me that that numerator I can rewrite as 1 over cosine squared of theta. And secant is the reciprocal of cosine, so this left-hand side then simplifies to secant squared of theta. And I have shown that that identity is in fact true. I manipulated only the right side to get it to match that, or excuse me, I simplified only this left-hand side to get it to match that right-hand side. Now here is a list of all the identities that we have talked about so far. We've talked about our Pythagorean identities. We have shown that these three are in fact true. We've talked about tangent, secant, cosecant, and cotangent, and our even-odd identities. Now these even-odd identities are going to come into play later in Chapter 6. So we will be referring back to these shortly. Okay, we have a few more complicated identities that we are going to verify. Now on this left-hand side, I do see two different functions that are containing fractions, and on this right-hand side, I see two different terms that do not contain fractions. So what I'm going to do to simplify this left-hand side is I'm going to start by getting a common denominator and seeing where that takes me. So I'm going to multiply the denominator by cosine, and then I have to multiply the numerator by cosine. In my second fraction, I will multiply numerator and denominator by sine of theta. So on the left, I will distribute. I've got cosine theta multiplied by sine theta, minus, when I distribute cosine to cosine, I've got cosine squared of theta. And in the denominator, I have cosine theta times sine of theta. Plus, in my second fraction, I distribute that sign. So I've got cosine of theta multiplied by sine of theta minus, and then I distribute sine to sine, and I have sine squared of theta. In the denominator, sine and cosine, I've got cosine theta multiplied by sine of theta. And we want to show that this is equivalent to 2 minus secant theta cosecant of theta. So I have a common denominator on the left, which means that I can add these two fractions. I've got cosine theta, sine of theta, and then I add the numerators. So in the top, I've got cosine times sine, which I can add with cosine times sine. So I have two of these. And then I have a negative cosine squared, and I also have a negative sine squared. We want to show that this is equal to 2 minus secant cosecant. So from here, what I see is that this looks very familiar to a Pythagorean identity, except the Pythagorean identity is cosine squared plus sine squared. They're both positive. Well, since these are both negative, if I just factor out a -1, then I will be able to rewrite that component of my fraction using a Pythagorean identity. So -1 cosine squared theta plus sine squared theta all over cosine times sine. Now cosine squared theta plus sine squared theta, I can rewrite this component using my Pythagorean identity. So now I'm going to take this piece and rewrite it to be just 1, because we know that that is what that expression is equal to. So 2 cosine theta sine theta minus 1 times 1 over cosine theta sine theta. I'm going to go ahead and cover this up so I can give myself some more space. I am trying to show that this is equal to that right-hand side, 2 minus secant theta cosecant theta. So on the left, I'll continue simplifying 2 cosine theta sine theta minus 1 over cosine theta sine theta. Now I do see that the cosine theta and the sine theta can reduce, but unfortunately, I can't reduce them right now because I have a -1 in my fraction. So I'm going to go ahead and split these up into two separate fractions. So then I have a -1 over cosine theta sine theta. Now this allows my cosines and my sines to reduce in that first fraction, which leaves me with just the 2 that I see as part of what I'm trying to get to. So I have the 2, and then the rest of my expression is 1 over cosine theta and 1 over sine theta. So I'm going to go ahead and split these up into two separate fractions with multiplication. If I simplify these down, I will get back to just the 1 over cosine sine. And the reason I'm doing this is because I know that cosine is the reciprocal of my secant function, and sine is the reciprocal of my cosecant function. So I'm able to simplify these down into the two expressions that I'm looking for. So I was able to take my left-hand side of my function, of my expression, and simplify it all the way down. I focused only on manipulating that left-hand side to get it all the way down to matching that right-hand side of my identity. So I have shown that, in fact, the left-hand side is equivalent to the right-hand side, meaning that we have verified this identity. I'm going to clear this now so that you can see the second example on this page. I would like for you to take a moment to now complete this second example on this page and then continue on to example 612 and 613 in your notes. You will know that you've completed it correctly when the left side matches the right. Thanks for watching.